Testing, can you hear me? Testing again. Okay, I'm testing my voice one more time. Alright, this video is public now, so I'm going to be learning about introductory statistics again. Last stream, wait, hold on. Last stream I was learning about descriptive statistics, but I did not complete the chapter. Okay. So I learned about descriptive statistics, about histograms, uh, frequencies, time series graph. I think I stopped at box plot. This is what I'm going to study now. Box plots, also known as box and whisker plots or box whisker plots, give a good graphical image of the concentration of the data. To construct, use a horizontal and vertical line number and a rectangular box. The smallest and largest data values label the endpoint of the axis. First quartile marks one end of the box, the third quartile marks the other end of the box. Approximately the mid 50% of the data fall inside the box. Whiskers extend from the end of the box to the smallest and largest value. Okay, so I'm guessing it's something like, so here's the data. Here's the data. Here's the smallest value. Here's the largest value. Let's say here's Q2 and here's Q1 and let's say here's Q3. The box plot would be something like this. And then endpoint. Then I think we have to mark the middle value also. Yeah, that's what they did. That's it, right? For some sets of data, some of the largest values, smallest value, first quartile, median, and third quartile may be the same. For instance, you might have a data set in which the median and the third quartile are the same. In this case, the diagram would not have a dotted line inside the box displaying the median. The right side of the box would display both the third quartile and the median. Okay, I think this is the median and the third quartile at the same time. The smallest and first quartile were both 1. The median and third quartile were both 5. The largest value was 7. The box plot would look something like this. In this case, at least 25% of the values are equal to 1. 25% of the values are between 1 and 5 inclusive. At least 25% of the values are equal to 5. The top 25% of values fall between 5 and 7 inclusive. Test scores for a college statistics class held during the day are this, and during the evening they're this. We have to draw a box plot, right? Find the smallest and largest values, the median, the first and third quartile for the day class. Yeah, we'll just focus on the day class for this exercise. 2.24. So I will just align it left. 70. 56 goes up here. 78. 99. Is that 55.5? 32. 90. 80. 81. And then 56 again. 59. 45. 77. 84.5. 84. 70. 72. 68. 32. Then 90. So we have smallest and largest 32 and 99. The median, the first and third quartile. So wait. Nope. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. The median is this, right? 72. So 1 to 9, including this. So there are 9 scores here. 21 to 20. No, wait. Median is between 72 and 77, right? So between 20 and 12, there are 9 numbers. Between 9 and 1, there are 9 numbers. So the median is 72. Wait. The median is between these two. So okay. Wait. How will I write? How do I show that it's not part of the data? I'll just draw a box plot. 32, 99, 72. So 2 plus 7 is 4.5. 74.5. I don't know. So here, 74.5. So we have uh, we take the last 10 values and then the first 10 values. Sorry, first 10 and the last 10, and we find the median between these, which is 6, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4. You have 10 here. 1, 2, 3, 4. 1, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So between 5 and 6 is 56. 1, 2, 3, 4, 5, 6. 56. And then is this 82.5? Yep, 82.5. 32, 56, 74.5. 82, 56, 72.5. 82.5 and 99. Okay. The center of a data set is also a way of describing location. The two most widely used measures of the center of the data are mean and the median. Calculate the mean weight of 50 people, add the 50 weights together and divide by 50. To find the median weight of 50 people, order the data and find the number that splits the data into two equal parts. Median is generally a better measure of the center when there are extreme values or outliers because it is not affected by the precise numerical values of the outliers. The mean is the most common measure of the center. The words mean and average are often used interchangeably. The Greek letter mu represents the population mean. The letter used to represent the sample mean in an X is an X with a bar over it, around X bar. One of the requirements for the sample mean to be a good estimate of the population mean is for the sample taken to be truly random. You see that both ways of calculating the mean are the same. Consider the sample. So we have this mean. In the second calculation, the frequencies are 3, 2, 1, and 5. You can quickly find the locations of the median using the expression n plus 1 divided by 2. The letter n is the total number of data values in the sample. Wait, how will this help us find the median? Do they mean the index? Will this help us find the index? The letter n is the total number of data values in the sample. If n is an odd number, the median is the median value of the ordered data. If n is an even number, then the median is equal to the two median values added together divided by 2 after the data has been ordered. For example, if the total number of data values is 97, then the median is the 49th value in the ordered data. The total number of data value is 100. Then n is 50 plus zero point 0.5. Median occurs midway between 50 and 51st value. Location of the median and the value of the median are not the same. Uppercase letter M is often used to represent the median. Another measure of the center is the mode. The mode is the most frequent value. There can be more than one mode in the data as long as those values have the same frequency and the frequency is the highest. Datasets with two modes is called bimodal. I'm guessing 72 is the answer here. The law of large number says, and if you take samples of larger and larger size from any population, then the mean of the sample is very likely to get closer and closer to mu. Mu is the population's mean, right? This is discussed in more detail in the text. You can think of sampling distribution as a relative frequency distribution with a great many samples. Suppose 30 randomly selected students were asked the number of movies they watched the previous week. The results are in the relative frequency table shown below. If you let the number of samples get very large, relative frequency table becomes a relative frequency distribution. A statistic is a number calculated from a sample. Statistic examples include the mean, median, and mode, as well as others. So, what's the difference between a distribution and the table? Distribution is like how the values in the entire population is distributed, right? Distribution is for the population, the entire population. When only grouped data is available, you do not know the individual data values. Therefore, you cannot compute an exact mean for the dataset. What we must do is estimate the action mean by calculating the mean of the A frequency table. Frequency table is a data representation in which grouped data is displayed along the corresponding frequencies. To calculate the mean from a grouped frequency table, we can apply the basic definition of mean. Mean is equal to data sum divided by number of data values. Simply need to modify the definition to fit the restrictions of a frequency table. Since we do not know the individual data values, we can instead find the midpoint of each interval. The midpoint is lower boundary plus upper boundary divided by 2. We can modify the mean definition to be, so frequency m divided by total frequency. Frequency of the interval, midpoint of the interval. So a frequency table is a data representation in which group data is displayed along with the corresponding frequency. So we have this frequency and then midpoint. Okay, so we do 4 times the midpoint, right? Then 4 times the midpoint, 2 times the midpoint. So the midpoint here is 3.25. Wait, hold on. Yes, 3.25. 6.5 minus 62.5. 59.5. Okay, and then we do F times M, frequency. So taking the midpoint and multiplying it by frequency. Consider the following data set. This data set can be represented by the following histogram. Each interval has width 1 and each value is located in the middle of an interval. The histogram displays a symmetrical distribution of data. A distribution is symmetrical if a vertical line can be drawn at some point in the histogram such that the shape, the left and right of the vertical line are mirror images of each other. Okay. The mean, median, and mode are each 7. Wait, what? Are each 7 for these data. Okay, 7 is the most frequent, 7 is in the middle, and 7 is the mean. That makes sense. In a perfectly symmetrical distribution, the mean and median are the same. This example has one mode. The mode is the same as the mean and median. In a symmetrical distribution that has two modes, the two modes would be different from the mean and median. Oh, I see. You can have a histogram that looks like this. Here, here. Imagine they're the same bit. One, two, three, 4, 5. In this case, this is the mean, and this is also the median, but these two are the mode. What's the symbol they use for mode? Let me see. So X bar for sample mean, mu for population mean, M for median, and these are symbols for mode. A histogram for the data is not symmetrical. The right hand side seems to be chopped off compared to the left. So there's more on the right compared to the left. Distribution of this type is called skewed to the left because it is pulled out to the left. Skewed to the left. Wouldn't it make more sense to call it skewed to the right? Skewed. Like, I don't understand this phrasing, skewed to the left. Skewed to the left means the left side has less data. Notice that the mean is less than the median, and they are both less than the mode. The mean and the median both reflect the skewing, but the mean reflects it more so. The mean is 6.3, the median is 6.5. The histogram for the data is this data is also not symmetrical. It is skewed to the right. So the left side contains more data. The mean is the largest, while the mode is the smallest. Again, mean reflects the skewing the most. The mean is the largest. The median is the 7.5. Okay. So between the median and the mean is closer to this side, right? The mean would be closer to the exact middle, right? If you ignore the frequency. The mean would be closer to the middle value if you ignore the frequency, right? And the median would be farther away than the mean. The mean is affected by outliers that do not influence the median. Therefore, when the distribution of data is skewed to the left, the mean is often less than the median. When the distribution is skewed to the right, the mean is often greater than the median. In symmetric distributions, we expect the mean and median to be approximately equal in value. This is an important connection between the shape of the distribution and the relationship of the mean and median. It is not it is however true for every it is not however true for every dataset. The most common exceptions occur in sets of discrete data. Skewness and symmetry become important when we discuss probability distributions in data chapter. Statistics are used to compare and sometimes identify authors. Following list shows a simple random sample that compares the data counts for three authors. Terry shows what? Letter counts. Terry, Davis, Maris make a dot plot for each of the three authors and compare the shape. Terry's letter as in what kind of letter? Like a mail, they get. Calculate the mean for each and calculate the median. 3.7, 2.7, and 4.6. The median is 3, 3, and 4. Describe any pattern you notice between the shape and the measures of the center. So 3.7, 3.7, and 3. So Terry's letter count is the most, sorry, no, Davy's letter count is the most skewed to the right, right? 2.7 and median is 3. Actually, no, Terry's letter count is the most skewed to the right. And Davy's letter count is more like it's skewed to the left. It's not all the way till here. And Mary's letter count is very close to symmetric, but these two kind of ruin it. So Davis's median is 3, 2.7. Okay. It appears that the median is always the closest to the high point, the mode, while the mean tends to be further out on the tail. A symmetric distribution, the mean and median are both centrally located close to the high point of the distribution. Measures of the spread of data. Important characteristics of any set of data is the variation in the data. In some dataset, the data values are concentrated closely near the mean. In other datasets, the data values are more widely spread out from the mean. Most common measure of variation or spread is a standard deviation. Standard deviation is a number that measures how far data values are from their mean. The standard deviation provides a measure of the overall variation in the dataset. Uh, Standard deviation is always positive or 0. Standard deviation is small when the data are all concentrated closer to the mean, exhibiting little variation or spread. Okay, so I mean, we have data like this. The mean is over here. This is more spread out. And if we have data like this, and this is less spread out. So I mean, if the data values are like x1, x2, x3, x4, so on, if these are the data values, we can check how far they are from the mean. So some xi minus this. But the thing is, but the problem with this is we will take this distance added with this distance added with this distance, adding the distance and so on. But there will be negative distance over here. So all the negative distance plus all the positive distance will equal to 0. Since we are calculating distance from the mean, distances from all the positive side will cancel out with the different distances in the negative side. So what we will do is that we will square it. We will square it. We will add all the squares of the distance. So one thing we can do is add only the modulus of the distance. And then, so the sum of all the distances over here, the sum of all the distance over here will be doubled. And then we can divide it by 2. So they won't cancel out now. Or it's easier to do math with squares than it is with modulus. Square. We can take the square of the square distance of from all of them, add them all up, and then square root it at the end. That will make more sense because it's easier to do math with square. No, I think we don't do square root. We just do square. And then this can, the more spread out the datas are, the bigger this value. The less spread out the data are, the smaller this value. But I need to revise it again because it's been quite some time since I learned it. The lowercase letter s represents the sample standard deviation, and the Greek letter sigma represents the population standard deviation. Symbol x delta is a sample mean, and the Greek symbol mu is a population mean. A data value that is 2 standard deviations from the average is just on the borderline for what many statisticians would consider to be far from the average. Considering data to be far from the mean, if it is more than 2 standard deviations away, it is more than 2 standard deviation away is more of an approximate rule of thumb rather than a rigid rule. In general, the shape of the distribution of the data affects how much of the data is further away than 2 standard deviation. Okay. They did the sum of this. Sum of the mean. Yeah, and I forgot the last bit. You have to divide it divided by n at the end. Because if the spread is the same, but I just add more data values, this value will keep getting bigger and bigger, so I need to divide it. But shouldn't I square root it first? Should square root it, right? If x is the number, then the difference x minus mean is called its deviation. In a data set, there are many deviations as there are items in the data set. The deviations are used to calculate the standard deviation. If the numbers belong to a population in in symbols, a deviation is x minus mu. The sample data deviation is x minus x. Yeah, x minus x bar. The procedure to calculate the standard deviation depends on whether the numbers are the entire population or are data from a sample. Calculations are similar but not identical. Therefore, the symbol used to represent the standard deviation depends on whether it is calculated from a population or a sample. The lowercase letter s represents the sample standard deviation. The Greek letter sigma represents the population standard deviation. The sample has the same characteristics as the population, then S should be a good estimate of sigma. The variance is the average of the squares of the deviations. The symbol sigma square represents the population variance. Population standard deviation is square root of the population variance. This over here is the variance. The variance, let's say this is population. So this is called a variance, represented like this. Symbol S square represents the sample variance. Sample standard deviation S is the square root of the sample variance. If the numbers come from a census of the entire population and not a sample, when you calculate the average of the squared deviations, find the variation. To find the variance, we divide by n, the number of items in the population. The data from a sample rather than a population, when we calculate the average of the squared deviation, we got divided by n minus 1. Okay, so for the population, I understand. For the sample, I don't get it. Why is it n minus 1 and not just n? The statistics of sampling distribution was discussed in descriptive statistics measure of the center of the data. How much the statistic varies from one sample to another is known as the sampling variability of a statistic. Suppose I choose a sample so large that it's very close to the population. Wouldn't it make sense to have this as n, not n minus 1? We typically measure the sampling variability of a statistic by its standard error. Standard error of the mean is an example of a standard error. It is special standard deviation and is known as the standard deviation of a sampling distribution of the mean. We'll cover the standard error of the mean in the chapter The Central Limit. The notation for the standard error of the mean is sigma over root n. Sigma is the standard deviation of the population and n is the size of the sample. The deviations show how spread out the data are about the mean. The data value 11.5 is further away from the mean than the data value 11, which is indicated by the deviation. Positive deviation occurs when the data value is greater than the mean, whereas a negative deviation occurs when a data value is less than the mean. Deviation is minus 1.525 for the data value 9. We add the deviations, the sum is always 0. If you add the deviations, the sum is always here. Not simply add the deviation to get the spread of the data. Squaring the deviation, you make them positive numbers and the sum will also be positive. Variance then is the average squared deviation. Variance of a squared measure does not have the same units as the data. Taking the square root solves the problem. Standard deviation measures the spread of the same units as the data. The variance is a squared measure and does not have the same units as the data. Taking the square root solves the problem. The standard deviation always measures spread in the same units as the data. What they haven't explained is why we divided by root n and not just why do we square root the n as well? Shouldn't we square root just the sum and then divide it by n after? Note that instead of dividing by n is equal to 20, the calculation divided by n minus 1 because the data is the sample. For sample variance, we divide by the sample size minus 1. Why not divide by n? The answer has to do with population variance. Sample variance is an estimate of the population variance based on theoretical mathematics that lies behind this calculation. Dividing by n minus 1 gives a better estimate of the population variance. Okay, they need to elaborate more on this. Standard deviation S or sigma is either 0 or larger than 0. Describing the data with the reference to the spread is called variability. Variability in data depends on the method by which the outcomes are obtained. For example, by measuring or by random sampling. The standard deviation is 0. There is no spread. That is that is all the data values are equal to each other. Standard deviation is small when the data are all concentrated close to the mean and is larger when the data values show more variations from the mean. When the standard deviation is a lot larger than 0, the data values are very spread out about the mean. Outliers can make S or sigma very large. Standard deviation, when first presented, can seem unclear. By graphing your data, you can get a better feel for the deviation. Standard deviation and the standard deviation. You will find that in symmetric distributions, the standard deviation can be very helpful, but in skewed distribution, standard deviation may not be much help. The reason is that the two sides of a skewed distribution have different spreads. In a skewed distribution, it is better to look at the first quartile, the median, and the third quartile, the smallest and largest values, because the numbers can be confusing. Always graph your data. Recall that for grouped data, we do not know individual data values. We cannot describe the typical value of a data with precision. In other words, we cannot find the exact mean, median, or mode. We can, however, determine the best estimate of the measures of the center by finding the mean of the grouped data with the formula Fm divided by F, the total frequency. Just as we cannot find the exact mean, neither can we find the exact standard deviation. Remember that standard deviation describes numerically the expected deviation a data value has from the mean. Frequency Fm delta. How did they calculate this? 7.5. Oh, but this is just the mean calculated using this formula. Fm divided by the total, right? So 1 by 26. 1 by 26. I don't understand. 1 divided by 26. 1, 4, 7, 10, 13, 16. 1, 4, 7, 10, 13, 16 divided by 6, right? 1, 4, 7, 10, 13, 16. 1, 4, 7, 10, 13, 16. by finding the mean. No, it's 197 divided by 26. Yeah, now that makes sense. Calculating the deviation, calculating the square, and then f times the deviation. This deviation appears these many times, right? So then we have to multiply how many times those deviation occurs. Squared deviation occurs. And then divided by n minus 1 and then square root it. Still don't understand why n minus 1 is inside the square root. Standard deviation is useful when comparing data values that come from different data sets. The data sets have different means and standard deviation, then comparing the data values directly can be misleading. For each data value, calculate how many standard deviations away from its mean the value is. Use the formula value is equal to mean plus number of standard deviations times it by standard deviation. So what are we calculating? How many standard deviations away from its mean the value is. Number of standard deviations is often called a z-score. So x is equal to the mean plus z is what we are calculating times s, right? So how many standard deviations away from the mean is x? Z-score is minus 2.1 and z-score for Ali is minus 0.3. For any data set, no matter what the distribution of the data is, at least 75% of the data is within two standard deviations from the mean of the mean. At least 89% of the data is within 3 standard deviations. At least 95 is within 4.5 standard deviations. This is known as Bishop's rule. For a data having a distribution that is bell-shaped and symmetric, approximately 68% the data is within one standard deviation of the mean. Approximately 95% of the data is within two standard deviations of the mean. More than 99% of the data is within three standard deviations of the mean. This is known as the empirical rule. What exactly do they mean by bell shaped? Oh, they give the thing below. By bell shaped, they mean distribution is bell-shaped and symmetric. We will learn more about this when studying normal or Gaussian probability distribution. This is just an exercise. Okay, this here. All right, this is the end, and the next topic is about probability. But if anyone can tell in the comments why is divided by n minus 1 and not n, that would be great. All right, then. See you guys next time.